Okay, so what light does to matter can be captured using a very elegant mathematical model, considering the fact that we just saw that the electromagnetic wave with an electric field of E naught I omega t, which we are experts in writing down by now, can drive the electron cloud and displace it from its equilibrium position x c of t, okay, and it can make it oscillate as a function of time, right, and the light wave's amplitude is varying harmonically in time, okay, that is it is sinusoidal or cosinusoidal. It's the light waves electric field is the real part of what we have written down here. Then we can simply use the sound principles or the bright principles of classical physics and write down what we physicists would call an equation of motion, or a simple differential equation, linear differential equation in this case, which can be solved provided we know some basic aspects of the system, as m a, which is from Newton's second law, okay, is equal to some force, okay, the Lorentz force as we call it from electrodynamics, and this alone would possibly have been sufficient, but here the electron is not free, it is bound to the atomic nucleus, which basically keeps the electron under check, and the electron nucleus system, the nucleus having a positive charge, are bound together. So, there is a notion of a restoring force in the whole process, okay, and which is written down. So, the acceleration is the sum of two forces, the external force and the restoring force natural to the system, plus some energy can be lost somehow in the process, it can be absorbed by the atom. To take care of absorption, when that is to say when the energy is being transferred from the electromagnetic wave to the atomic system, which is the electron cloud times the nucleus plus the nucleus, so to say, is captured by the damping if there is any absorption at all at a given frequency. So, this differential equation can be solved fairly straightforward, it is a matter of undergrad physics, and the electron's displacement x c of t for any given value of t, every given value of t that is of interest here, can simply be captured by following factor, which has two parts to it. One is the input wave itself, E naught of t exponent of I omega t, okay, which is one factor, multiplied by what we would call the response function. In this case, it is E, the charge of the electron, divided by its mass, E by m, divided by omega naught square. Omega naught is a factor which we use to define the restoring force of this atomic system. It is a spring mass system. So, omega square is related to the spring constant. If you wish, consider if we build an analogy to a mechanical spring, omega is the frequency of the driving electromagnetic field and gamma is the damping coefficient, gamma is here the coefficient in the damping term. So, it is written down, simply written down, it is a forced simple harmonic oscillator. It is a simple harmonic oscillator with damping and a driving force or a driving field. We may call it a forced oscillator if we wish. Now, the electron oscillates among all this at the frequency of the incident wave. Okay. Now, does that ring a bell in our minds? I am going to jump a couple of notches, but show you this animation, that since the charge of the electron is not plus, but a minus E being the elementary charge, it is a fundamental constant. Okay. Only quarks can have fractional charges, but then they always come in triplets, which form further fundamental particles called protons, which have totally a total charge of plus E, and matter is electrically neutral, the charge of a proton and the charge of an electron balance out to extraordinary levels of precision or accuracy, right. We have not found any charge imbalance in matter. Even if we find a very tiny imbalance, remember there is an Avogadro number of 10 to the 23 across units sitting there. So, a tiny imbalance would actually mean a huge amount of effective sort of charge and whatever not. It is a fascinating physical principle to think about, but E is the elementary unit of charge. Now, it is minus times E is always a positive number which is measured in coulombs, right. So, it is 1.6 times 10 to the minus 19 coulombs numerically. So, because there is a negative sign, the negative sign is e to the plus of e to the I pi is minus 1. So, there is a pi out of phase motion, there is a pi out of phase motion between the oscillations of the electric field and the electron being driven, but the point being that the motion of the electron and the field that is driving both oscillate at the same frequency omega. Now, this is all we know about matter. This is a classical model, but even quantum mechanically it again comes down to solving this oscillator problem in the presence of the electric field, and the solution to the problem for the displacement of the electron cloud turns out to be identical, okay, although the interpretation of this could be different. Okay. So, no matter what, the take home message is electrons and the charge that is oscillating can only oscillate at omega if the driver is driving the system at omega. Okay. So, with a little bit of a leap, I can say the following, that this entire phenomenon is also linear. Did you find any powers of 2 in any of this of the equation anywhere? Watch carefully except for omega. In anything concerning x, is there any power of 2? d2x by dt2 is the second derivative to the first power. Here dx by dt is first derivative to the first power, x to the first power, electric field to the first power. So, the entire physics is linear. Okay. So, the part of the wave that propagates through this gas of atoms can have two components: a part of the initial wave that is not absorbed and transmits through, and a part of possibly another electromagnetic wave emitted by this oscillating electron cloud, because accelerating electrons must emit radiation. If the electrons are also oscillating at frequency omega, the frequency identical to that of the incident electromagnetic wave, they will also emit, if they emit electromagnetic waves, which they do, emit an electromagnetic wave again at frequency omega, the same frequency. So, where is all this leading us to? Even without a very rigorous proof, this tells us that there can be only electromagnetic wave in this description of light matter interaction, okay, can occur only at one frequency, the driving frequency of initial driving frequency of the initial electromagnetic wave, which is omega, right. So, it is for this reason that when you first learned the subject, your instructor or teacher told you that, look, when light propagates through a medium, the frequency does not change, whereas wavelength, okay, in the medium is wavelength in vacuum divided by the refractive index, and the velocity in the medium is the in vacuo speed of light, or the speed of light in vacuum divided by the same number. Okay. And we were told C is not V but nu times lambda, or V is again the same nu, here it is vacuum because C is in vacuum, here it is lambda of the medium. v, the velocity of light in a medium, is nu, its original and unchanged frequency times the velocity. Okay. Now, we know that light is slowed down in a medium as compared to vacuum, okay, as we pretend as though we measured both the velocities, but at least in thought experiments we do, if not in real. Now, therefore, nu and lambda must adjust, the product must adjust itself to give v. So, who is going to compromise? Is nu going to compromise it, or is it lambda, or are both going to contribute to the depreciation in the value of the velocity of light? Physics earlier, without understanding the from a fundamental picture what happens in light matter interaction, we just took this as a mantra. If you wish, that frequency does not change, so wavelength has to, but now we have a robust understanding of why the frequency remains constant. The frequency is unchanged because the interaction is linear. It is a consequence of the linearity in the interaction of light with matter that frequency remains a constant. Okay. That point must be made, and to appreciate the constants of frequency, we need to appreciate the model that underlies, or the physics that underlies light matter interaction, even at a fairly basic level. Okay. So, now this is what light does to matter is the question that we can now answer in some detail. Okay. The forced oscillator's response is sinusoidal, and the relative phase, okay, what is the phase relative to? The relative phase between the displacement of the electron cloud vis-a-vis the driving electric field, both of which are time dependent quantities, and we saw that both of them are sinusoidal, right. So, this is one sinusoidal function, and this xc of t is another sinusoidal function. The solutions told us that there is only one oscillating term, time dependent term in this equation, which is the basically the complex exponent. Likewise, over here, right, these two are going to oscillate with respect to each other, but they are mediated by a coefficient which is essentially a complex number, E by m divided by omega naught square minus omega square minus 2i omega gamma. Okay, it is a complex number. So, we can write this in its polar form, the amplitude times e to the power I the phase. So, since we have an e to the power I phase, x of t and e of t are out of phase. By definition. Okay. If there is a sign, e has a negative sign, so that can add a constant e to the power I pi multiplying the whole thing, but that is, be that as it may, we understand that they are out of phase by pi due to the sign of the charge, but is it just that? Are the two always out of phase by just a factor of pi? Okay, that is exactly anti of each other, if you wish, right. That is, if one goes down, the other goes up in a naive picture, or is it something else? Yes, it is more than that. Therefore, we can consider three scenarios, one where the driving frequency omega of the wave that is forcing the atom to do something, okay, versus omega naught, the natural frequency of the electron nuclear system, the spring related to the spring constant of this bond. These two can be compared. If the driving frequency is much less than omega naught, let us call it the eigen frequency, eigen the German word for principal, main or important or whatever, right. We know eigen value, eigen frequency. So, omega naught is the natural frequency, the eigen frequency of the system. If the driving frequency is much less than this, then from the expression above we can knock off omega, because it is much smaller than omega naught. Okay. Omega naught square is much greater than omega square, and that is kind of greater also because omega is a small number unless gamma turns out to be huge, which it is not usually the case. We can simply erase all these terms in the denominator when omega is much smaller than omega naught, and realize the fact that when omega is much smaller than omega naught, the oscillation or the excursion of the electron cloud is pi out of phase, or the electron cloud vibrates 180 degrees out of phase with respect to the light wave. This is exactly what we depicted in the previous case. They are sort of oscillating pi out of phase. Okay. They are in perfect disagreement, if you wish. However, let us consider the other extreme where omega, the driving frequency, is far greater than omega naught. What happens then? It is obvious. We can carry a negative sign from the denominator, we then knock off the omega square terms containing omega, or rather we can knock off the omega naught squared term, take that out, the denominator is negative definite, if you wish. Omega naught square is negative, omega and gamma are positive numbers. So, the denominator's negative sign carries forward. There is also a negative sign right up there. In this condition, the electron vibrates in phase with the light wave, okay. Kind of counterintuitive. We just said, oh, it has a negative charge, so the motion should be pi out of phase. No. What determines the relative phase between the two is not the mere sign of charge of the electron, it is indeed the relationship between the driving frequency omega and the natural frequency omega naught of the system. Okay. Omega naught is an important quantity, it is the characteristic that is specific to every atomic, molecular, condensed phase, semi condensed phase, nanoscale, low dimensional system, or any fancy version of matter that you bring must have one or more natural frequencies omega naught, and it can depend on many other details too. It can depend on the direction of the polarization of the wave maybe, or even the state of polarization, right circular, left circular, the direction of the k vector, and does the beam have any finite orbital angular momentum, and whatever not. It can depend on a whole lot of factors, even subtle factors, be that as it may, but it must have a certain value that is different from one scenario to another. So, omega naught is a key player in this game. Okay. So, with that being the case, we of course must ask, what if there is perfect agreement between omega and omega naught? If there is perfect agreement between omega and omega naught, then we have, whenever two frequencies meet in physics, it is a happy thing, or at least we can pretend it is that way, we have resonance. All right. This resonance is a very interesting scenario, and this is where we can see one very important thing happening. What we can see happening is that both the quadratic terms in the denominator in omega vanish, okay, and we essentially have, for the first time, gamma has some role in our life, in our description. Gamma has an important role, and in this case we essentially have something happening. Okay. It is a factor of I, it is purely imaginary, okay, over here. So, we must note that as well, and this is going to play an important role. We will see what that means in some time. However, the important factor to realize is that we have minus I become multiplying the E of t, xc of t is minus I times E of t, and minus I is essentially e to the power I pi over 2 is minus I. So, both of them are out of phase by, in this case, minus 90 degrees, minus I pi, right, minus I pi over 2. Therefore, they are out of phase by 90 degrees, minus 90 degrees, so to say, right. So, in this case, this is a very important fact of life, that at resonance, you can remember this as an adage, the driver and the driven are, we always say pi by 2 out of phase. This is very important. The driver and the driven system are both, the motion of the driver and motion of the driven system are pi over 2 out of phase. Okay. You can anticipate an assignment question on this, or if I may take the liberty of saying something like that. It can also be cast in fairly subtle forms, so beware. Yeah. So, personally I had an encounter with this as a PhD student in a different context, but it was in a fairly subtle way. It was one of the most important learnings as an outcome of my PhD, which in some sense you could have said you learned in high school. But yeah, subtlety is the thing. This concept can manifest itself in our lives as physicists and engineers and scientists in many ways. So, it is worth putting it on a t-shirt if you wish. Yeah. So, basically if we could even like visualize this by saying, hey look, if the system is below resonance, that is below, resonance is omega naught, omega is below, omega naught is above, and omega is below resonance, this is resonance. Then you have pi over 2 out of phase motion between the driver, which is the electromagnetic wave, and the driven system, the electron clouds motion. Now, if the two are on resonance, life is maybe balanced somehow or whatever, they are here, the factor by which they are out of phase is pi, this is minus pi over 2. Okay. In terms of the two, the interesting thing here is when they are in resonance, the amplitude, okay, the amplitude is the strongest, the vibration amplitude is the strongest. We will discuss that in a sec. Whereas, above resonance, they are both in phase, but the vibration of the two things is kind of in phase. Okay, that is omega is much greater than omega naught. They are 0 out of phase. Okay, if you have 3 animations on a screen, it's too much action for the movie, but the point is made. But why is the vibration strongest at resonance? Easy to see, very easy to see. Look at these denominators. When in the two other cases there is an omega naught square or an omega square dividing the entire thing, that quadratic quantity omega or omega naught in the optical case is a number as large as 10 to the 14 per second. Okay. So, if that goes away and there is still a multiplicative factor of omega in this case, but then there is also a gamma. Gamma is not that large a quantity numerically speaking. Okay. So, we have made the point that omega and omega naught are much larger than gamma typically, the damping constant. Okay. That is why it is damping, it is a weak phenomenon compared to a strong natural frequency. That is why we call it damping, and that is why the motion is also simple harmonic, right. So, considering this nuance of the forced, damped, forced yet simple harmonic oscillator, we encounter the fact that the vibration is strongest, vibration as in the displacement of the electron is strongest at resonance. So, that point is also well made. We can also view it in another context, as I said, using a spring mass system. This is pretty much the same. I must credit my colleague Thomas Fennell from the University of Rostock for sparing us this very nice animation of, which is a realistic calculation of how the electron cloud in this classical simulation oscillates when an incident electromagnetic pulse, a femtosecond pulse of the type that we have considered with a central wavelength of 800 nanometers, when it is incident on a metallic nanoparticle, say made of silver atoms. So, this is how the electron cloud oscillates. Okay. These are actually plasmon oscillations, if you so wish, but this is really the point that we wish to make. It does not matter what is the underlying thing, a single atom, a nanoparticle, whatever. The concepts of being at resonance, above resonance, below resonance are both, are all important. As at resonance, we can also say over damped, under damped, likewise in terms of oscillator physics, right. So, what we can now do is take the response of the atom, which is essentially the basically it is xc of t, which is a function of time, and put this through this has a complex coefficient. Okay. The response of the atom is proportional. Now, we focus our attention not on the harmonic oscillation, but the prefactor which contains matter specific information in the form of omega naught and gamma. These are matter specific information. Now, we look at this and we want to write this now in terms of a real part and an imaginary part. Okay. Separate this into an a plus ib form, if you wish, a typical complex number. So, in any case, if we, in order to do this efficiently, if I may use such a term, let us make a simplifying assumption that since omega and omega naught are both substantially large numbers, especially when compared to gamma, let us say that these are approximately equal. Okay, that is to say, both are optical frequencies, both are infrared frequencies. It is not that one is optical and other is sort of microwave. We are not considering such scenarios. That is simply because you can find an omega naught at every region of the spectrum for most materials. If you are talking about omega naught in the microwave, omega in the microwave, there is an omega naught which is pretty close to it, which is the omega naught that matters in each case. Okay. So, therefore, consider it is a very reasonable assumption to make that omega and omega naught are pretty close to each other, in which case omega plus omega naught can be approximated to twice omega, and but we should not force omega minus omega naught to 0. Let us write this difference, which we can call delta, to be the detuning, if you wish, between that is the frequency difference between omega naught, the natural frequency, and the driving frequency, which is in our hands. Driving frequency is of course in the hands of the physicist or the experimenter. The way we have defined it here is omega naught minus omega. We should keep track of the sign. Then in terms of the, we can write this in terms of the complex variable now delta, okay, and the function now is a complex Lorentzian. Okay. 1, now we can write this function as 1 divided by omega minus omega naught, the delta, minus I gamma. Okay. 1 divided by delta minus I gamma. So, now we can separate this out efficiently in terms of its real and imaginary parts by multiplying and dividing this quantity by delta plus I gamma, okay, and then we get 2 components to it. The real part is delta by delta square plus gamma square, the imaginary part is I gamma divided by delta square by gamma square. Delta and gamma are both real numbers, okay, and we are having to deal with their squares, the sum of their squares in the denominator. So, the denominator is a positive quantity. This brings us now to the following description of things, where we can plot the real and the imaginary parts as a function of delta. We do not plot it as a function of gamma, because gamma is fixed for a given material or a system matter. Gamma is fixed for a given piece of matter, as also omega naught is also fixed. Both these are fixed for a given physical scenario, although there could be multiple omega naughts and multiple gammas that one may have to deal with in a system, just as we had multiple spectral lines from for the same given atomic gas or material or matter or whatever it is, that we will encounter this again, but I am just making the point here that they are fixed, but they need not be just one pair of numbers. Okay. Then the real part is delta by delta square plus gamma square. Imaginary part is gamma divided by delta square plus gamma square. Okay. So, now the imaginary component has a very nice form. Okay. It does not have a variable in the numerator. So, here we should make the point that delta is the variable of interest in this entire scenario, right. Delta is the variable of interest. We plot the real and imaginary parts as a function of delta, okay, and this plot is now a nice quantity. The imaginary part you can clearly see is an even function, okay, as a because only delta is variable and we just have a delta square. So, the imaginary part is an even function. Sorry, the y got slipped off here, that is probably not good view graph stuff. So, let me obscure that, okay, for the moment. Y, so, the imaginary part is an even function, whereas the real part is an odd function. Okay, the real part is plotted in violet in this plot. Let me still use a yellow highlighter to lace that a bit. It has this very characteristic S shape, whereas the imaginary part is very symmetric. It is not Gaussian, it is for an atom, single atom, the response is, according to this notion of classical physics, it is Lorentzian. Even in quantum mechanics this is true. Okay. Atomic line shapes are fundamentally Lorentzian. But if you have scenarios where you have to add a set of Lorentzians together, it can approximate to a Gaussian, a gas of atoms in which atoms are moving with a spread of velocities, Maxwell distribution. So, that can lead to a Gaussian looking line shape. A single atom is, its natural line shape is Lorentzian for these type of resonances. There could be other types of resonances where the shape can change, some of which go by the name of Fano resonances, which we are not considering in this discussion. Okay. So, this is a very fundamental aspect of light matter interaction and very important to our understanding, and this is indeed we are making our way to the physical understanding, the physical origin of refractive index. You need to look no deeper than this for most purposes.